Hello and welcome to the final electricity session at ENIC 2020, where we'll be covering smarter asset management. I'm Dr. Geraldine Patterson, Innovation Manager with Electricity North West, and I will be your host for the session. We're about to hear about 5 exciting innovation projects that are being led by Northern Power Grid, my colleagues at Electricity North West, National Grid Electricity Transmission, UK Power Networks and SP Energy Networks. If you would like to ask a question during these talks, please do so using the text chat facility at the right of your screen, and our speakers will do their best to respond to you. To get the best experience, we recommend that you close all other applications on your computer and check that no one else is using your broadband connection.
Hello everyone, my name is Ross McFarlane, Innovation Project Manager at Northern Power Grid, here today to talk to you about the Silent Power Innovation Project. I hope that you're enjoying the ENIC 2020 conference this year. And by way of an introduction, I just thought I'd start by telling you a little bit about what we do here at Northern Power Grid. So we are the distribution network operator in the North East, Yorkshire and North Lincolnshire, serving 8 million people across 3.9 million homes and businesses. And we own the vast majority of all of the substations, overhead lines, underground cables in the area, and we're available 24/7 to fix the network in the event of a network fault. So the electricity industry, as I'm sure you know, the energy sector, is facing a number of challenges at the moment, one of which is decarbonisation and how we go about decarbonising the energy sector in the UK. And that's where we're going to talk about Silent Power today. But as an organisation, we are continuing to invest and innovate in the electrical network to make sure it's fit for purpose in the future. So in terms of the problem that Silent Power is trying to address, at Northern Power Grid, we deploy a significant number of diesel generators each and every year in order to restore customer supplies in the event of a network fault and also to maintain supplies during a planned power interruption. Now, the use of diesel generators in this manner is generally considered inefficient, and that's because they are sized for the peak load onto the network to which they're being connected. And that means for the vast majority of the time which they are connected, they're running way below their optimum operating threshold. And as a result of this, the running costs, the CO2 emissions, the noise are all relatively high when you compare that to a more efficient form of generation. So Silent Power was a way for us to explore whether an electrical energy storage system would deliver benefits to our customers and also to our field staff. Now I have a short video that I would like to share with you where you'll be able to see the Silent Power unit out there in the field on a real life deployment, and it'll hopefully add some meat to the bones in terms of my explanation.
Silence is golden. From the minute it leaves the depot until it pulls up on a customer's drive.
Hello there.
Hi, Mr. Johnson.
Yes,
It's Will from Northern Power Grid.
Oh, you couldn't put some electric on, have you?
That's the plan, yeah.
But the silence doesn't stop there.
It's one of our biggest issues is the complaints we get about, yes, you've restored my supply, but my neighbours are complaining about the noise. That's all going to go away now.
There's no noisy generator, there's no pollution, and there are no fuel leaks. It looks red, but it's green, very green, and fully self-contained.
Historically, they've been on trailers, which might be slightly more difficult to manoeuvre and get near to customers' properties.
We've miniaturised the unit to increase the power electronics and used a newer generation of batteries to develop the system that you now see. We always want to have a tangible benefit there at the end for customers through all of our innovation projects.
I think I worked for 35 years with the electricity board. I had a long, enjoyable career. With the old-fashioned generators, there was a lot of maintenance involved, and you had to have someone come along and keep topping you up with diesel fuel. No noise, and it's just sitting there like a car, and brilliant.
Musician Tom Gascoigne has multiple sclerosis. He relies on electricity to get around his house and work.
Everything I do needs power. I can't function in the day without electricity.
He's played at hundreds of outdoor festivals and knows just how noisy generators can be.
It's a bit like somebody using a lawnmower whilst you're trying to talk. So I'm fully aware of the shortcomings of but I used to use them, so if there's an alternative, wonderful.
The silent power van can maintain power for 2 households for 24 hours. But like all technologies, advance will be rapid.
The battery density improves all the time, and it's totally scalable, so you can put more batteries into a bigger vehicle and get more power. This time 10 years ago, you didn't have everything on your phone, so it can only move forward.
Silent power is good for customers, good for the environment, and good for the people who keep us connected.
I've worked in the industry 40 years, so seen a lot of innovation, and I've got to say this is one of the good ones.
So if we were to open the doors on the silent power vehicle, you would see that there was 3 main components to the system, and that is the batteries, the inverter, and the telematics system. And to give an idea of scale, the batteries are about the size of a microwave, and there's 5 of them in the system. And the telematics and the inverter are about double that size again, but there's only 1 of those each in the system. Now, I think we're all comfortable with our understanding of what a battery does, and that it's a device that stores chemical energy that it is able then to convert into electrical energy. And the batteries which we use are manufactured by an organisation called Hyperdrive Innovation, who are based in Sunderland, and they use Nissan lithium-ion cells, and it's actually the same cells which are used in the Nissan Leaf electric vehicle. Now, because batteries supply a DC voltage, we've used an inverter to convert that DC voltage into an AC voltage, which is what, of course, our customers' properties require. And we've also paired the system with a telematics unit, so we can monitor the state of charge at the system, the temperature of the different cells, all remotely, so we can assess how the system is holistically performing. And all of that equipment was sent to another organisation called Off-Grid Energy, who are based in Rugby, who built the unit, and it's rated at 25 kilowatt hours and has a 40 kV output. Now, we expect that unit, the silent power unit, will be able to maintain supplies to a maximum of 3 residential customers over a 24-hour period. And that is assuming that a residential customer uses somewhere in the region of 10 kilowatt hours over a 24-hour period. But at the end of this project, it's going to be really interesting to find out whether that assumption actually held true. So throughout the project, the biggest issue that we have had to overcome is the gross carrying capacity of the electric vehicle that we use to house the electrical energy storage system. That has caused us to lose some functionality that we had originally planned to include within the design phase. So if you were to look in the back of the van at the moment, you would realise that there's physically more space to build a bigger unit, which, as I say, we just didn't have the gross carrying weight in order to do that. So on reflection, I think it would have been easier to do this project probably using a diesel transit van, which has a much greater carrying capacity. But I think when you're doing an innovation project, you always need to be mindful of the story that you're trying to tell. And it wouldn't really sit right with me that we would invest all of this money in an electrical energy storage system to deal with decarbonisation and then simply drive it out of sight in a diesel transit. That just wouldn't really sit right with me. So in order to overcome this issue, we reduced the battery payload capacity from 30 kilowatt hours to 25 kilowatt hours, and also used a newer generation of batteries from Hyperdrive Innovation, which have a greater energy density. So we could get away with using 5 battery units from them as opposed to 8 because of that greater energy density. But the reduction from 30 kilowatt hours to 25 kilowatt hours also meant there was a reduction in the number of residential customers that we thought we could supply. And we had also at the design phase planned to include a small petrol motor to recharge the batteries during times of low demand. So the idea with that was, in the morning when the kids went off to school, parents went off to work, the system would sense the drop in load and the small petrol motor would kick in, and during the day when nobody was at home, recharge the batteries. And then when people returned at the end of the working day and the load started to pick up again, the system would sense that and snap back over to the batteries to give that clean, silent supply to the customers. But again, because of the weight restriction, there was a lot of auxiliary equipment included with that piece of functionality. It was unfortunate that we just had to lose that at the time. Silent Power has been a great project in that it has given the Northern Power Grid innovation team a tangible piece of kit that we could take along to events and conferences and strike up a dialogue with our stakeholders about our innovation portfolio and the work that we're doing around decarbonisation. At the 2018 LCNI conference, we took along the prototype Silent Power unit, and it was really interesting to have those conversations with people who maybe didn't work necessarily within the industry and talk them through the project, what we were trying to do, and hear their take on how they thought the unit could be used. I specifically remember a conversation with an individual who worked for a chain of hotels, and he was explaining to me an issue that they had with some of their hotels in rural communities, whereby guests would drive to the hotel in their electric vehicles and then expect to be able to charge their electric vehicles once they got there, which is a very reasonable demand. But unfortunately, this is not always possible in rural settings, whereby the electrical network may not be as robust enough to facilitate electric vehicle charging. And when I was telling them about the Silent Power project, they thought that this was a great way of having a mobile solution that they could drive around to different hotels and use it to charge up electric vehicles. And this is just simply not something that we had envisaged for the unit during the plan phase. So it was really interesting to get that different perspective on how the unit could be used. Another high point for me was at the beginning of lockdown, when Silent Power was used to restore supplies on a fault to a pharmacy. And I was really pleased that we could play our part in supporting that local community at what was a very challenging time. And we also received really positive feedback from our field operatives about how simple the unit was to connect to the pharmacy and how reliable it performed once it was connected. Silent Power can assist with the journey to net zero in a number of ways. The big advantage, of course, with Silent Power is that it doesn't need any diesel. So there's no associated fume or particulate contamination, and the risk of a fuel spill is completely mitigated. The system is also bi-directional, and what that means is where a customer may have a PV installation on their roof, we can use that energy to recharge the batteries in the Silent Power unit, so we can connect the unit for a longer period of time. And this is just one example of how we are investing in the use of microgrids to support the electrical network. We've also worked very closely with our diesel generator service providers throughout this project, and it's really encouraging to see that they are now making innovative technologies commercially available themselves. The use of variable speed generators and hybrid systems are all slowly but surely coming online in a commercial setting. But in terms of where the project is headed next, as I mentioned earlier, the maximum carrying capacity of the electric vehicle that we used in this phase of the Silent Power project had caused us a few issues and had caused us to lose some of the functionality that we had originally planned to include. In terms of next steps, I would like to repeat the project using a diesel transit vehicle. So we have a larger carrying capacity, and we can build back in that functionality that we unfortunately had to lose in this project. So we'll certainly keep you posted on any developments with the project. But that's the end of my presentation now. I hope you have enjoyed it, and there's been some information in there that you can take away, that you can, I hope it's been useful. If anyone has any questions though and would like to continue on a dialogue with me, I can be contacted at ross.mcfarlane@northernpowergrid.com. But I just want to say thank you very much for spending some time with me today, and I hope you enjoy the rest of the conference. Thank you.
Sentinel is a fault detection and location system, effectively a radar system that's constantly monitoring the performance of the overhead line. It's looking to detect the normal, traditional sort of low impedance type faults, as well as those which are basically those faults that cause high currents to flow. But one of the main aspects of Sentinel is that we're trying to also develop the technology to identify very dangerous situations where an overhead line conductor can come away from its support and actually pose a serious risk to the public. Traditional faults on the overhead line are detected, or faults on the overhead line are detected using traditional protection systems. And following a fault, engineers are sent out to identify the location. This in itself can be costly, time consuming, and most importantly can also be dangerous to staff and to the public. This obviously has an impact on customer minute lost and also poor customer performance. Sentinel aims to be able to locate a fault within a couple of 100 metres of the actual location. This therefore will reduce time to identify the fault, enable us to get crews to the right location quicker and repair the fault and get customers back on supply much earlier. So being able to locate the fault, get there quicker, means obviously customers are off supply for shorter periods of time, which also reduces the customer minute lost figure and improves that. Now in terms of a loss of life, you can't put a value on a loss of life, and hopefully this technology will show that we can do that. The technologies deployed within Sentinel include impedance-based and voltage gradient technologies, as well as signal injection using TDR. This is the technology that will detect the low clearance lines. Effectively, it's a digital pulse that is constantly sent down the overhead line, and depending on the reflection of that signal, a change will be seen. So on a normal line, if you like, it has a fingerprint. So this pulse will continue every couple of seconds down the line and come back, and that reflection basically overlaps itself if it's healthy. So every reflection will come back on that line and should remain the same. Where there is a change, which is a discontinuity within the line, will be seen by a change from its normal, shall we say, and from that point we can measure where that is on the line. It's all pole mounted equipment. Basically you have a control box, no different to, looks like a GVR type control box, and then above, connected to the overhead line, is a voltage divider and a current sensor. Normally, depending on the type of fault, obviously if it's a fault that's caused protection relay to operate and hence trip a device, then you know it's beyond that point. We also basically no supply. So those type of faults that cause protection devices to operate, we know within a certain area where that fault may lie. And yes, it's still time consuming. Depends on the terrain of where these are, because overhead lines go through forests, valleys, cross water. So usually the terrain, or in a lot of instances, the terrain can be quite dangerous and difficult. So there's also, and then there's also those faults that we call transient faults, faults which don't cause protection devices to operate, and basically we rely on customers to phone in and say they're off supply, and from this, depending where those customers are, we can identify that a non-telemetry device may have operated on the network, say fuses, because we don't know whether fuses operate within the HV control room. Then in terms of the dangerous situation I was talking to before about the low line, at the moment in time, the only way we can identify those is by the public calling in and saying that they've seen something. In those instances, what we would do is we would dispatch an engineer immediately, and we would also identify off the HV network, as well as using geographical tools to identify that HV circuit, and we will actually make that dead to ensure safety of the public. Apart from actually being able to reduce customer minute loss in terms of your high current, low impedance type faults, it's better customer service. You're removing danger from staff going out to identify and locate these faults. But what the most important thing is the safety. Basically, this system could prevent the loss of life where where a low line scenario occurs. This is one of the most dangerous situations that can be posed. So as well as looking at the actual development of the sensors themselves, we also had to look at where to deploy them. So we came up with we had to work on a criteria to understand the best locations for the devices. Following this assessment, we decided to actually put as many devices on the trial circuits as we could to ensure that we captured all the data we needed, and from there in the future to look at the optimization, how many sensors, and this was also dependent on the success of the technology itself and how far they could actually see down the overhead line. We identified 12 circuits actually. With these circuits were selected on fault history, because with it being a fault detection system, you want to actually have faults to actually prove the concept or prove the technology. And on those 12 circuits, we're looking to deploy a total of 150 units. To date, we've installed 110 units so far. We've got some down in the Peak area, down in Lancashire, and in Cumbria. So right across, trying to get that total, that diverse sort of topology across all circuits. Prior to installation, we also had to go through a number of trial installs at the Academy, as well as producing operational documentation and to provide training, not only for the linesmen, but also for the control rooms, so that the control engineers understood exactly what we were doing during outages when deploying and installing this technology, as it's new to, as it's completely new and never been trialled before. Unfortunately, after a period of time, we find problems were identified with voltage drift problems with a large number of the sensible devices. What we've identified is that the voltages have been drifting up or down. Basically, we found that due to the environments in which these devices are installed, that we've had to deploy additional environmental protection within cable connections and additional earthing kits as well. So with these solutions in place, we have now been back to upgrade a total of 30 units, and we are happy to say that these solutions have actually worked successfully, and we're now into a period of deployment of actually upgrading the remaining of the initial installed 110 units. All devices then should start triggering on whenever there's a fault on the network, or should there be a change in characteristic like the lowered line scenario from its fingerprint. So all this development has been undertaken by Kelvotech at this moment in time, and developing those algorithms is a very, very difficult it's very, very difficult, and they're working round the clock constantly to refine these algorithms. Unfortunately, refinement only comes from tests and results, so the more faults we have, the more data they have, the better the algorithms will become. And this is sort of thing that will go on forever. As we do get more and more faults, even in time, even if it does get deployed as mass deployment across the whole network, then they'll be for always refining the triggers and the algorithms on these. So in November 2019, we carried out HV faults on the overhead line. These included phase-to-phase and phase-to-earth tests. These faults were most successful, and the software was able to detect to an accurate location within 100 metres of the actual fault that was applied. Earlier this year, we carried out a low line test where we lowered, again in controlled manner, the HV conductor of one phase to 1 metre and 2.5 metres above ground. Once the line was re-energised, the data was collated from all the devices within that trial circuit. What's come out of those results is that the algorithms at this stage were not sensitive enough to identify the change in electrical characteristics as the line was lowered, and as such Kelvitech are now going through a refinement of those algorithms. We'll also be carrying out further controlled testing ourselves by applying faults to the network to accelerate that learning, shall we say, to ensure that we have sufficient data to prove the concept by the end of the project. Without that, it won't be able to go forward as a project, so we need to have that confidence that it works. With things being controlled, we can choose areas of the network where we don't actually have to knock customers off, or very few customers off. To improve that and to help us, we've actually developed a test platform which will be on the back of a low loader that we will be able to drive around to overhead lines and position in, well, depending on access, such that we actually we have less of an impact on customers. Just been built as we speak now. It's been designed, approved, and hopefully we will be taking that round to a number of locations to apply further faults. So where are we today then? So at this moment in time, we're in the process of carrying out an upgrade program to resolve the voltage drift issues that we've faced. We've got another 32 installations to carry out. A dashboard has been created, a live dashboard, which is basically a fault tracker, has been developed by Kelvitech as well. This is a web-based system which identifies all the trial circuits, all devices on those circuits, and will identify problems associated with each of the devices. So hopefully we plan to complete the upgrades and installations by at the latest February 2021. With the project being extended to 2022, this gives us in excess of a year to hopefully have sufficient number of faults to prove the technology, and also enable us to continue to refine the algorithms. As faults occur in the network, and we are advised by Kelvitech, we will feed back to Kelvitech what we find on site. This is a process which will help us to define the algorithms further to hopefully reach the target of faults within 50 metres or so. It wasn't part of the project at this moment in time to have real-time reporting. It's basically proving the concept at this stage. However, there is another phase of the project which is implementation of Sentinel into the network management system, which will be close to real time. This is all based on the development of the algorithms and the triggers to operate in a very short period of time. So what we're doing in the interim is applying a soft approach whereby Kelvitech will develop the algorithms, and it'll be a reporting system. They will, from Belfast, they'll phone in or email into the control room with details. We're looking at the functional specification for that at the moment, so we anticipate them to be able to contact the control room within 5 to 10 minutes of a fault. So if you take a low line, for instance, at the moment, could be there for days, weeks. We don't know, because we're always relying on the customer or on the public to come and advise us. So in terms of this system, whether it was 24 hours or 12 hours, in terms of developing those algorithms, that would still be a huge saving in time, but we expect that to be within the minutes. But once we've proven the technology, we will then go into a further development period where we'll look at changes we can do to this existing system. This trial is just basically proving the concept of the off-sensor. It does what it says on the tin, if you like, and if we are successful, we will move to that BAU solution.
Thanks everyone for joining my presentation today at the ENIC on one of our projects in National Grid, Project Osiris, which is about optimized infrared image scans. Really appreciate you attending today and taking the time to listen to our presentation. If you want to learn more, please do get in contact. Quite a simple presentation today. Three key sections. The driver, why are we doing this project? What did we do on the project, or what did the team do? And what the outcome was. So the project driver. So in general, infrared images are used to identify temperature differences on various assets within the national transmission system. We use infrared pictures on all different types of assets, and generally that's seen as a good way to tell if there's a defect within a particular asset. We use that usually differentially, so we look at 3 assets in the same circuit, and we say, okay, are there temperature differences between phase red, phase yellow, and phase blue? And if there are differences, that seem to be a indicator of a problem. Many suppliers recommend the use of these cameras and thermal imaging as a method to detect defects, and it's certainly something that is seen broadly got application in our industry. So in general, the way the process works is that you take an infrared picture, you look for temperature differences. If there is a large temperature difference, you do an expert review, which could be simply someone looking at the data, someone visiting the site with new equipment or more equipment, or simply just repeating the same measurement again. We tend to take pictures from different angles, and that's an attempt to try and mitigate some of the uncertainties that we have in these images. It's recognise that the environment, the asset, and other factors can really influence the temperature readings that you get out of these assets. We also don't just apply these to cable sealing ends, which is all I've been showing so far. We apply these to many different types of assets. So what you can see here is some switchgear, but also we apply this to CTs and VTs, many different asset types within the substation and outside the substation. So it's a very broadly applied technique for defect and fault analysis. So the challenges that we generally faced was that when we looked at the data and the results of these scans, we found that there was many false positives. And what that did is it actually resulted in additional work, which obviously nobody wants, and also increased risk to individuals. So some of the mitigations or the follow-ons from these false positives were going out across the country and collecting more data. We knew that environmental impacts could mask signatures or could potentially mask signatures. And actually, when these are used in safety systems, it was really important to understand, okay, under what scenarios do those environmental factors prevent us from taking a good measurement? And there didn't seem to be a lot of information out there in this area. Our present system also made no accounting for the uncertainty in the measurement systems we do use. All measurements have uncertainty. It's a fundamental part of engineering and science, is all measurements do have uncertainty associated with them. And I think the general question we were faced was, how do we scientifically set a threshold on what constitutes an important temperature difference to improve our readings and to improve the way we manage our assets with infrared cameras? So that's really the driver what we do and what the driver is for this project. So what did we do? Well, quite simply, we started an NIA project, and really simply, the project had two main aims: to understand the potential sources of uncertainty in our measurements in greater detail, so we can understand when we were and when we weren't making valuable measurements. And we also wanted to propose mitigations to reduce that uncertainty. If we can reduce the uncertainty, we can then reduce the false positives, and that improves everything across the business. So really important we looked at this. But not just for National Grid, but I think for many other utilities who get the same recommendations that we do. So what did we do? Well, actually, we set up some long-term infrared camera monitoring. So we set it up on 2 different assets, and we took repeated images of these assets over several weeks. We then collated that data and looked at what the natural variations were in the readings, and used that in conjunction with weather data to understand the impact that environmental factors can have on these measurements. It also gave us a good insight into the sort of distances we were dealing with, angle measurements, and the different geometries, all of which affect these infrared images. We also took a camera and the shed of a ceiling and put that in the lab. We tested the camera into quite depths against an international temperature standard, and that allowed us to understand, what was the inherent uncertainty with those cameras. We then were able to take that camera where we knew the uncertainty of the camera itself, and then we looked at an asset that we would be looking at in the field. So we'd be looking at the shed of a cable ceiling end. What we then also did is applied a known heat source and well-calibrated temperature measurements to the asset, so we could see when we're putting heat in, how much temperature did we get out? How hot did this thing get? And that really gave us some deep insights into the thermal behavior of the assets, differences between internal and external temperature variations, the stability of the temperature, the stability of the asset, and the impact that the asset geometry, the distance between the camera and the asset, and the angle between the camera and the asset under question has on the measurements, which were really important factors that we wanted to investigate further. We were also able to take some measurements as part of one of the DSITE projects, so we had a really great opportunity to leverage some learning from another project that was going on where we had a known defect in one of the assets, and we took measurements where we have a known defect in one asset and known where there's no defect in the other, that provide a really strong comparative analysis. And it was a really great opportunity to leverage learning from this other project. So we took the opportunity to do that as part of this. So what's the outcome then? So we've got all the data, we've done some tests in the lab, and we've looked at what we do as a process. What does this mean? What's the outcome? Well, I can't go through all the details, as there's 4 or 5 reports which utilities are welcome to look at as part of this project, and we're really keen to share the outcomes. But I'll just take you through some of the highlights from my point of view. So changing distance and angle really matters. When you start to take temperature measurements. Simply changing the distance from 2 meters to 3 meters, we saw increase the overall uncertainty by around about 3 degrees C. And changing the angle from 0 to 30 degrees, also between the camera and the asset, also increased the uncertainty by an additional 3 degrees C. Now that's not 3 degrees C of uncertainty on its own, that's over and above the uncertainty that we were seeing from the tests we did on the camera themselves. So it's an increase in uncertainty of 3 degrees. For each one of those factors. Size of source is a really important consideration for our application. Generally, you need the thing that you're trying to measure in an infrared image to occupy a significant proportion of the image. However, in our application, that's not possible. If you're trying to take measurement of 3 assets, you simply can't have all of them occupying more than a third. And actually, at that sort of 30% level of occupying the image, you start to get serious impacts from size of source effects, which can really degrade the quality of that measurement. Generally, if you've seen very much at the moment with the COVID measurements, they're taking a thermal imaging reading, they come very close to your forehead, and they take that image, they take that reading, occupying the entire image space, as it were. And we see that in our application, actually, we can't do that because you can't get that close to the assets, and that has a really detrimental impact on the uncertainty in the measurements. We also looked at varying camera parameters, looking at how things change when you change the settings. It's important to remember that these are not visual light cameras; they are slightly different. And what you have to do, you have to create the image. So what you're doing as part of the processing of the data is you're creating an image out of readings, and the processing and the algorithms that are used to create that image can lead to misleading readings. So everything in these 2 images is at exactly the same temperature, plus or minus about 0.1 degrees C. The room that these tests were done in is very well controlled from a thermal point of view. And what we found was that when we changed the settings about how that image is created, you end up getting misleading visual readings to a user. And this can lead to uncertainties. Very difficult to quantify in terms of an uncertainty budget, but is a really important point to highlight, is that we are fabricating an image out of data, and the methodology and processing used to create that image is important and can lead to fake hotspots appearing in your image. So really important outcome of the project. The cameras, sensors themselves have natural variation, and this is to be expected. Not every manufacturing process is perfect. You can't recreate things identically every time, and certainly as things degrade over time, things will vary. But in the world of thermal imaging, actually, there's more factors you have to consider. So the uncertainty in the materials themselves, rolls around about the 2 to 3 degree mark, but actually that changes with time. So each individual pixel inside that sensor has a time varying variation with it, which makes it complex. This also means that if you rotate the camera, so if you're not just changing the angle at which the image is taken to the asset, if you rotate the camera, you're using different sensors to pick up the same, to measure the same asset, which can increase the measurement uncertainty further. Temperature of the asset also really, of the camera itself, also impacts its uncertainty. So simply leaving the camera in the sun or in a warm room and then taking it outside or being outside for longer can have an impact on the uncertainty. And as the camera takes readings, it heats up itself. It's absorbing infrared radiation, and all of that ends up impacting the uncertainty. And that's what we saw. We saw certainly with these cameras. You can see here an image of the data where we have. We've plotted that out, and we've shown that you get this variation over time in the digital readings that are output by those centers. So it's really important to understand this, is that you might be seeing variations in your image which are not really there. The project did produce an uncertainty budget. It produced a couple of different ones depending on which settings of the camera used and which processing algorithms, and it also looked at potential mitigations, and there's a full list of those in the project. But generally what we saw is, for our application, based on the 8 factors that we scientifically quantified, is that the uncertainty at 95% confidence level was around about plus or minus 30 degrees. This can be reduced with proper data management and with some more structured data gathering, but only to within the limitations of the camera itself. You can't go beyond that. For the differential analysis, which is a big question that we were interested in, that did reduce some of the uncertainties, but those uncertainties were much smaller than some of the other uncertainties, which it ended up increasing. So the impact of using differential analysis to say, is red phase hotter than blue phase, actually increased your overall uncertainty and is more likely to lead to false positives being generated. So a really interesting outcome for us, a really interesting outcome, I think, for the industry as well. So in conclusion, thermal cameras have a significant uncertainty, and the application matters. The cameras themselves have uncertainty, and when you take them out of the lab and you start to use them in service, the application and how you use it and what you're looking at really impacts that uncertainty. It's not a small amount, it can be significant. Data quality measures can improve this. Finding a structured way to collect that data and using different processing algorithms can improve the uncertainty, but only within the limits of the camera itself. There is a limit, which for us in this project and the cameras we were looking at was at about plus or minus 10 degrees C. So even if you did all the best processing algorithms, you could not get better than that. Size of source effects need to be considered very carefully when you're taking these measurements. If your asset is far away, more of the reading that you're taking is coming from the other assets and other things in the image. Everything emits infrared radiation, and the smaller your asset is in that image, the less information is coming from that asset and the more is coming from the background environment. So it's really important to scientifically consider these things. Thresholds need to be carefully set to what constitutes a fault and what doesn't, or a defect and what doesn't. Uncertainty can range into the tens of degrees, which means those thresholds need to be very carefully considered before they're set. And certainly we're looking at updating our settings as an outcome of this. Differential analysis can increase uncertainty, leading to more false positives. It's a technique which is pushed forward as a way to reduce overall uncertainty, but if you're not careful, it can increase uncertainty, and knowledge of those of the uncertainties in your system are really important and really do make a big difference. Supplier recommendations as well is something that should be taken very carefully and should be carefully considered with physics and engineering properly to understand, is what I'm doing giving me a meaningful measurement, and is that going to help me improve the situation? So thank you very much for tuning in today. I hope you found my presentation exciting. If you do want to find out more, my name's Dr. Oliver Sikowski, and I work in the National Grid Innovation team. Please do get in touch. Thank you.
Hi, welcome all to ENIC. My name is Joe Colbrook. I'm part of the innovation team here at UK Power Networks. My job is a workstream lead in the innovation team. I help deliver many of the innovation projects that we do. In particular, I work on active response and a number of other smaller NIA projects. It's critical that we fund and research innovation here at UK Power Networks to help us reach net zero. But it's also really important that we're there for our customers in the here and now. And that means that we have a reliable, safe network with the best customer service every day. And we also achieve this at the best possible value. These new projects will build on the company's continued efforts to reduce the frequency and duration of power cuts. From 2011 to 2019, the network operator almost halved the number of power cuts, meaning people only experience a power cut once every 3 years on average. Supplies are 99.9% reliable. These projects all test innovative technologies to either predict power cuts before they happen or give engineers more information about faults while the power cuts happening and help us restore them as quick as possible. These projects include installing 16 fault application devices at 7 electricity substations in Suffolk, Sussex, Kent and London. The devices detect, qualify and alert in real-time electrical disturbances on overhead lines and underground cables. Another project was trialling of new smart data algorithm in a project called Miles. This project runs till 2023. The Miles system uses computer software connected to a series of sensors to show engineers a fault location within just a few meters. Using software with British Geographical Society and Met Office that factors in rainfall, cable density and soil characteristics to create a heat map of where faults could arise a few days in the future, UKPN were able to allow engineers to prepare and react to faults much more quickly. So one of the projects that I helped deliver is called Storm Resilience. It's looking at 2 slightly different things, so it's split into 2 work streams. The first tool that we're developing is called Lightning into Power On, and it's all about trying to get our lightning data from a leading meteorology company directly into our Power On system, which is our energy management system. So we are working with GE to deliver this tool, and it uses an API to connect that data into our own systems. We then can use that data, the lightning data, to help us diagnose faults on our HV system quicker than we already do. So for example, this can allow us to detect if a fault is due to lightning and reclose the breaker within 30 seconds rather than the 30 minutes that it currently takes. So it's up to a 90% saving on the customer minutes lost that we have. The second tool is the resource estimation tool. So this is a tool that's using AI to forecast the number of faults on our network during a storm or weather event. By using this tool, our emergency planning team can work out where exactly we need to put teams and what extra resources we might need to deal with the potentially large number of faults. So overall, this helps us reduce the time our customers are off supply.
Hello, my name is Chino Atako, a Senior Asset Engineer at UK Power Networks. I have been in the industry for about 15 years. I joined EDF Energy Networks in 2005, and in that time have gone on to hold several interesting roles, mostly in asset management, so from inspection and maintenance and compliance, to asset replacement strategies, to preparing justification and papers for the Distribution Price Control Review Period, DPCR5, to my current role in the Network Risk and Performance team in UK Power Networks, looking at quality of supplies and fault management strategies. In my current role in the Network Risk and Performance team in UK Power Networks, we work closely with our colleagues in the innovation team to identify and implement solutions that enable us improve our quality of supply performance and reduce the impact of faults on the network. One of the exciting solutions, which I'm excited to share with you today, is the solution being trialed on the project HV feeder monitoring to preempt faults. The project is a collaborative project between UK Power Networks and Scottish and Southern Energy Networks, and is funded by the Networks Innovation Allowance. The aim of the project is to demonstrate the proof of concept that it is possible to identify leading indicators for faults, such that we can move from a reactive fault management process, which is the current approach, to a more proactive fault management process. Central to the project is the trial of distribution fault anticipation devices alongside fault passage indicators to try and identify pre-fault events. The distribution fault anticipation solution was developed in the United States and has been used extensively in some utilities in the US, Australia, and New Zealand over the last decade. The distribution fault anticipation solution is based on the idea that many types of faults are preceded by minutes, sometimes hours, days, or even months, weeks and months of pre-fault events before they actually manifest themselves on the network. Essentially, what we'd be trialing here is carrying out high-frequency waveform sampling and analysis of current and voltage waveforms on selected HV and 33 kV feeders. We then compare the disturbances observed in this process to a library of known disturbances that lead to certain types of faults. This library has been built up over the last decade for monitoring in the US, Australia, and New Zealand. Now, this process allows the DFA Plus devices to classify events as either normal or abnormal, or to identify particular types of faults that may be emerging on the network. If we think of the traditional approach to managing faults, DNOs would typically send crews out to respond to asset failures, to carry out repairs and restore supplies. However, by using this process where we're trying to identify leading indicators, we believe it's possible to move to a much more proactive approach by responding to notifications from devices such as the DFA Plus device to identify a probable fault location and to mitigate it before it manifests into a permanent fault. Typically, the DFA would provide an indication of the type of fault and a probable location based on other network information and from a bit of network modeling. In instances where the DFA identifies disturbances that are not present in its library, the DFA device still groups events that have similar characteristics over time. During the course of the project, we intend to provide a feedback loop to help us label some of these disturbances. So, for example, if we have a subsequent failure and can confirm what type of failure it was, we can always go back and label some of the grouped events that have been collected or saved by the DFA device. Typical faults that we can identify from this process include anything from animal-related faults, vegetation, or other contact type management, some asset breakdown of sorts, either through arcing or some other phenomenon. And we can also identify abnormal network conditions, such as harmonics on the network, or even network gradient issues. So, for example, in scenarios where reclosers or the devices on the network fail to operate. The project is a 3-year project. It started in 2019 and will run until 2022. And in that time, we intend to trial the solution on 16 feeders in UK Power Networks and another 16 in Scottish and Southern Energy Networks. What we hope to be able to do at the end of this trial is to demonstrate that it is indeed possible to identify pre-fault events and carry out proactive repairs. We intend to validate some of the notifications we get from the DFA devices and to prove some of the potential savings. The ability to preempt faults in the way that's being explored on this project has several benefits. So we know, for example, that proactive repairs are significantly cheaper than reactive repairs. It would also allow us to reduce customer interruptions and customer minutes lost. We know that this has a direct impact on the broad measure of customer satisfaction. So all in all, we're looking at benefits that would lead to reduced costs for DNOs and to customers, and improved customer satisfaction. We are excited about the potential outcomes of this project. And needless to say, the ability to move from a reactive approach to fault management to a proactive approach will be a paradigm shift in the way we currently run the electricity distribution networks.
Hi, my name is Peter Papasotiriou, and I'm really excited to be giving this presentation at ENIC today about fault location excellence and how UK Power Networks keeps the lights on as we transition towards net zero. Fault location excellence is one of our top priorities at UK Power Networks because we want to deliver the most reliable power supply to all our customers. We first aim to keep our network reliable by proactively looking to repair our network using methods which detect pre-fault conditions or transient faults. Where that is not always possible, we aim to reduce the duration of power cuts by finding and fixing faults quicker. We would like to share more about the projects that we're running in the innovation team, which will help address these aspects. A little bit about myself. I come from an electrical engineering background with portfolio and project management experience in the electricity and transportation industry. I am the Innovation Portfolio Manager within UK Power Networks, overseeing all NIA ENIC projects. At the moment, 2 of the innovation team's projects, Raffle and Miles, both have similar objectives in locating faults, but their methods are vastly different. The Raffle project, short for Radiometric Arc Fault Locating, is a collaborative project between UK Power Networks, SPEN, the EIC, and Olympus. Olympus are developing a really novel means of fault location. This method makes use of a network of devices which individually detect the radiometric signal of an arcing fault. The devices then send the waveforms of these signals back to a cloud server, and the Raffle algorithm then detects the location of the arcing fault. This method is similar to a lighting detection system, and we're trying to bring this innovation idea into our network. The project has recently completed its testing at the PNDC, and the initial results have been very promising, showing accuracy levels to within 100 meters. There are certainly challenges to it, such as overly noisy environments masking the signal, or terrain itself attenuating the strength of the received signal. So, with Chino's help, we're looking to deploy trials in SPN to enable us to assess the effectiveness of the system in our network. Our second project is called Miles, where UK Power Networks is partnering with CGI and Hydro-Quebec to deliver a new method fault location. Miles is a French acronym for Intelligent Maintenance of Electrical Lines, and it was developed by Hydro-Quebec in Canada. The underlying technology relies on a series of voltage sensors on the LV network, which detects a voltage drop across an 11 kV feeder when a fault occurs. These sensors then pass their captured waveforms to an algorithm to locate the most likely fault location on the network. Follow-on actions from this will allow UK Power Networks to perform targeted tree cutting and network maintenance or replacement. Initial analysis indicates that most faults could be located up to within 200 meters accuracy, and it is certainly hoped that we will see measurable improvements in network resilience. My colleagues Peter and Chino have been providing their expert advice on implementing this, and we're looking to bringing it to trials by the second quarter of 2021.
Thanks for listening, guys. I hope you've really enjoyed this presentation. You can get in touch with me at joe.colebrook@ukpowernetworks.co.uk. Have a great rest of the day. Cheers.
LV Engine is one of the flagship projects in innovation projects in Spain, and is about bringing flexibility and controllability in LV network. So the project started in 2018 after a successful submission of the proposal to Ofgem, and since then we've been busy obviously developing the project. So the main aim of the project is to develop a new technology, a new type of transformer which relies on power electronic technology. The technology we're designing and manufacturing, LV Engine, providing some of the core functionalities. It can control the LV network voltage very in a fine way, compared to OLTC, which is more coarse, basically, action. It can control the power flow coming to LV network. It can cancel the imbalance, basically load, and also it can provide LVDC supply. So LVDC has been studied in terms of feasibilities and the benefits of that, basically, for supplying low carbon technologies across the world. And being demonstrated on paper and some limited trials that can be beneficial to supply, such as something like EV chargers, directly by low voltage DC. In normal system, what's happening is we're converting AC to DC at the charging heads, and then converting DC to DC again, and then supply to the electric car, basically. But if we can eliminate the AC to DC initial conversion, so that in general, we can reduce the losses within the EV charging head, basically, And power electronics are not coming so efficient because of switching, because of other design aspects, they're always coming with some sort of losses. So by eliminating that, the whole unit is going to be more efficient and also less expensive, because you're eliminating a conversion stage, basically, in a charger, and make it even lighter and in terms of footprint, smaller. One of the milestones we achieved since the start of this year was we appoint a capable manufacturer through competitive tendering. So we have a manufacturing partner on board, and we started designing the details and how the product look like, how it's going to be interfaced with other plants, etc. So the design stage has been completed, and we have progress quite successfully in that regard. So, and then we are looking to start manufacturing the unit. So the way we have to design it to make sure it can sit within our substation and it can interface with other plants. My colleague David Walker would be able to give you more details about how this unit is going to be sitting with the substation and interface with other plants.
Well, obviously my involvement is to take this innovation project and support the innovation team to come up with a solution that can easily fit into a traditional substation. Not only the size of the substation, but also the typical substation environment. So some of the challenges with that is normally power transformers are a traditional 100-year-old technology where you have a metal box with an iron core, copper windings, and filled with mineral insulating oil as a liquid to provide cooling and electrical insulation. And what we're doing now is taking power electronics, putting them in a similar box, interfacing in a similar way by connecting power cables to that box, but making sure that that box meets the typical footprint that we've established over many years in our substation environment, and also can operate over the lifetime of the product in an environment that we became used to. So typically our transformers are manufactured for an outdoor environment, and they're basically kind of fit and forget to some extent. We need to do some maintenance from time to time, but normally there's not that much to do. Whereas power electronics, we don't understand if it has the same lifetime. So typically a mineral oil insulated power transformer can last 50, 60, 70 years in an outdoor environment. We're not sure if power electronics is going to last that same amount of time, especially in some of the environments that we have here in the UK. So we need to ensure the environment's correct for that technology, but also ensure that it can fit into what we would class as a typical substation. As a business, we're looking for a kind of black box solution. From my point of view, we need to make sure that interfaces are correct so that we can operate them safely as per our health and safety rules and regulations, but also that operators can terminate cables, can understand the logic of the information that's being presented from the control module. But as far as getting into the box itself, it's not something that we imagine that in service we're going to have to interact with. The power electronics will be similar to something that we're all used to, but just the same as we don't open up the chargers in the home environment, as a business it's unlikely that we're going to be opening up these transformers in service. If we have a problem, we'll probably return to our supplier to get that kind of technical support. And the box is going to be intelligent, so it's going to be able to look at what's happening on the network. It's going to be able to balance loads. It's going to be able to regulate voltage, and it's going to be able to provide functions that typical transformers don't give us. So normally typical transformers are deployed in a substation. They're not intelligent at all. They just supply a voltage which may go up or down depending on the load, and typically we can't control that, whereas this new power electronics technology will be looking out at the load, looking out at the network, and balancing the voltage dependent on the load, and can share the load between this substation and adjacent substations due to the interconnection that we'll have. So therefore, it does give us a lot more flexibility when supplying our customers.
I'm very optimistic that we're going to have a very exciting product, and lots of learning coming out of the project already, which we are reporting through various kind of reports. But all team excited when they see the development on the manufacturing side, on the designs we are doing on the trial sites. And it's a challenging project, but in the same time, kind of very, very exciting, and keep us going.
I would like to say a sincere thank you to our session speakers and all of you for coming along and participating in our Smarter Asset Management session. Although this session marks the end of our formal electricity conference at ENIC, you can still go ahead and visit any stand you may have missed in our exhibition and innovation halls, and come back again at any point in the next 40 days to play any of our webinars on demand or to download information from our stands. I hope you all enjoyed the conference, and I look forward to seeing you again at ENIC 2021.